Okay, so let me explain what how this condition. Maybe I'll explain it the other way, and then we can come back and fix the inequalities here. So we have this tableau here, and then we write down the reading word. So the reading word. So what you do is you read it in Hebrew. So you start from the right, and is that right? And move to the left, but you read it from top to bottom. So it becomes 2 1 2 2 1 3. So this is the 3 1. Oops, see, I keep switching to. Yeah. So the Hebrew reading word is going from right to left, top to bottom, and and so and so then what you want this to be is a ballot sequence. Okay, so this term also I need to explain. A ballot sequence means that it's a sequence of numbers where if you look at any initial segment, so any prefix from left, since we are using Hebrew, it's from left. Because if you do it the other way, that's called the reverse reading word, that doesn't correspond to any language that I know of. Whereas this corresponds to, Urdu, Hebrew, Arabic, and several languages. So this should be a ballot sequence, which means that in every initial segment, the number of i's should be at least as large as the number of I plus 1s. Oh, my board work is getting very messy. So yeah, let's just erase this, because anyway, this is what we want. So this is violated right in the beginning of this word, because if you look at the segment of size 2, the number of 2's is, no, just look at the segment of size 1, sorry. So let's just look at this first segment. The number of 2's is 1, the number of 1's is 0. So it's already violating this. So maybe you can help me to fix this and give me a word that will actually arise from that filtration problem in abelian groups. So can you give me, so what are my mu? So let's try to keep the weights the same. So let's try to so in this example, nu is 2 1's, 3 2's, and 1 3. It's not a partition. So maybe that's another bad thing. Let's since we're talking about partitions here, though you can do this, and that's also still called but let's change this to see, you can never have a ballot sequence like this, because at the very end the number of 2's will be more than the number of 1's. What? Yeah. So it will fail. So you can never have it like this. So maybe here what I should have done is have, let's do 3 2 1. So I want 2 1's, okay, so let's just modify it. The easiest change to be made, I could either change this to a 1 or I could change this to a 1. Which one should I change? Suppose I change this to a 1, just for the sake of example. Then the Hebrew reading word is 2 1 2 1 3 1. And this is not a ballot sequence, right? Huh? So the first row has to have only ones. That's otherwise, because that's what comes at the very beginning. Suppose I had this, then the Hebrew reading word is 112213. Oh, is this okay? So you just look at it, scan it from left to right. So, till here we don't even have any problems because, yeah. Yeah, so, huh? No. I'll give you something else. Yeah. So you have to read from right to left because you read from left to right, then 1, 2 would be allowed. We don't want that. Okay, so this is the okay, so this is called the Littlewood-Richardson condition. So T is called a Littlewood-Richardson tableau if um, its reading word is a ballot sequence. Another way to talk about this is to write the tableau in French notation and then just read the word in French. Okay, so, and then what happens? Then it has to be Yamanouchi. So, yeah. So there's all kinds of different ways of stating. And then there's the Russians who write it like at a 45-degree angle to everything, which Christopher forgot to mention in his talk. So anyway, it's a bit confusing at first, but after a while, you get used to it. So this is a very important condition. It's called the Littlewood-Richardson condition. And this appears in representation theory in a couple of places, which I will explain in the due course of this lecture. So, but the point is, suppose given, right? I'm given a group this, you know. So now I can ask, okay, so I'm given this this kind of a situation. I want to count subgroups of A lambda, okay? So this A nu is the standard copy of A nu. I want to count so I want to count subgroups of A lambda that are isomorphic to so this A nu is given a filtration like this, and I want to count the number of subgroups of A lambda that are isomorphic to A mu, where the quotient is um, the quotient is isomorphic to A nu with this fixed filtration, and the filtration gives rise to this semi-standard Littlewood-Richardson tableau. So given an so this is called an LR tableau, Littlewood-Richardson tableau. Given an LR tableau T, the number of filtrations, So a mu equals a mu 0 containing a mu 1 containing a mu n, and this is to be a lambda, right? So I'm looking for the number of such flags of subgroups with the property that, maybe I should not call this a mu, this is a, yeah, or yeah, such that, yeah, I was calling it a lambda I, right, such that a lambda I is isomorphic to lambda I. Is just, you can just compute it, is given by, well, you just have to see how much you can do at each stage. So you will get G lambda 1 mu nu 1, G lambda 2 mu nu 2 up to G lambda n, which is lambda mu nu this is nu 1. No, this is nu 1, this is nu 2. These are cyclic portions, nu n. So stage wise, you build the subgroup corresponding to each lambda. And this, what this construction does is it gives the quotient group a filtration, right? So we're not just so we will be overcounting. We will be counting the number of subgroups of type mu such that the quotient is of type nu and a filtration on the quotient group. But this is a polynomial of degree. So this is of degree n lambda 1. Remember, did I introduce this? N lambda is equal to summation I minus 1 lambda I for a partition I goes from 1 to L lambda I. And what you have is that this G lambda mu k, it has degree n lambda minus n mu. That's something that's, maybe we can do it as an exercise. That's easy to check. So it's a polynomial of degree. So now you'll have n lambda 1 minus n nu 1. So these things will, something's wrong with the denominators. These not denominators, these lower terms. So this is lambda 1 nu 2, right? These are the subgroups nu n. I think I've confused everyone completely here. Okay, so let me just back up a bit and tell you what we're doing. So what we're doing is we fixed an LR tableau, and what we're going to do is we're going to count the number of such configurations, right? And it's clear from what I said earlier that, okay, so at each stage we're just counting subgroups. Maybe you can start from the right and go left. And that number of subgroups is given by one of the coefficients that we actually already computed, which is a polynomial, but I should have written these things correctly. So so at each stage you have a group of type lambda I and a subgroup of type lambda I minus 1 and a quotient which is cyclic of type p to the nu I. So this is a polynomial. If you add up the degrees, you'll get n lambda 1 minus n mu plus n lambda 2 minus n lambda 1 and so on. And finally, all that will survive is n lambda minus n mu. Okay, and this polynomial is monic. because each of those polynomials is monic. So what we get is huh? Yeah, I'm starting with a Littlewood-Richardson tableau, shape lambda, mod mu, and content mu, correct. And then I'm counting the number of such things. Okay, so, but I don't want to count in so much detail, right? I just want to count the number of subgroups. I don't want to count all these filtrations. So I have to divide by the number of filtrations that I get for all such groups. So if I count all such filtrations, what I'm getting is of filtered, I'll call these filtered configurations is equal to sum over T belongs to LR. So I should call them LR lambda mod mu type mu. And then there's a polynomial, some polynomial which I'll call, I don't know, G, and this only depends on this tableau T times, yeah, that's it. But then I'm over counting, so I need to divide by the number of filtrations. And this is a polynomial of degree um, n nu. So what you get is you have a sum over all these things. So this so definition, the Littlewood-Richardson coefficient C lambda mu nu is defined to be the number of Littlewood-Richardson tableau of shape lambda mod mu and content mu. And what we get is that, so this is Hall's theorem, that G lambda mu nu is a polynomial in P with integer coefficients and all these terms have the same degree. So leading coefficient is C lambda mu nu times P to the power n lambda minus n mu minus n. So this Hall algebra is a very nice algebra. These a priori I had defined it over rational numbers or complex numbers, but now what I can do is I can define it as an algebra where the scalars are integer polynomials in P. Yeah.
Just check I got it. So GT is that monic polynomial that you get as a product of the G's.
Yeah.
Yeah?
Yeah. So that T completely determines those. It determines the parts of the filtered partitions, the stages in which you're constructing.
I'm just trying to
Yeah.
connect
Yeah. So this
the
only.
GT with what you've written.
GT is this product. So maybe I should have. Thanks. So oof, I'm running out of time. Okay, so that's the main theorem about the Hall algebra. But what we've seen is also that the HNs form uh, the HNs form a generating set. But once we've done this, we can also show that there are other generating sets. Not HNs, the UNs. The UNs form a generating set for the Hall algebra. But once we've done this, we can do another one. So here's an exercise which maybe we can do in the tutorial, that after doing all this, what you can show is that G lambda mu. So earlier we looked at K where a partition with one part. Now let's look at a partition where all the parts are equal to 1. So 1, 1, 1, 1, K ones. Okay. This is non-zero. So what we are going to do is, when is this non-zero? This is non-zero if and only if the Littlewood-Richardson coefficient is non-zero, right? So this is by what I said. So maybe I should add here that this polynomial is non-zero. I mean, it's sort of implicit in this thing here. Otherwise, the polynomial is non-zero. If the Littlewood-Richardson coefficient is 0, this polynomial is non-zero. It has no leading term, nothing. It's just 0. And so here, this is the same as saying that C lambda mu 1, 1, 1, 1, 1 is a Littlewood-Richardson tableau. So what is happening here is you're adding k boxes. And it has to be a Littlewood-Richardson tableau means that the order in which you're adding these, so the boxes will just have each number once, 1, 1, 1, 2, 1, 3, 1, 4, and so on. But basically you cannot have a k plus 1 to the, so this is the same as saying that the answer turns out to be lambda minus mu is a new word, vertical strip. So what that means is that you cannot add more than 2 cells in a row. Okay, so we'll do this as an exercise. Maybe during the tutorial you can remind me. Just good to get a feel for these Littlewood-Richardson tableaux. Okay, so what we can do now is we can, like we did, so we found that G lambda mu k is non-zero if and only if it's a horizontal strip. You can do this with a vertical strip. And now instead of using generators UN, I'll use generators U1111. Let's call this WK. And in the same way, you can show that Wn n greater than or equal to 1 generate the Hall algebra freely by proving another triangularity result with the reversed order. So this Hall algebra is a very nice algebra. It has two generating sets, the UKs and the U1111s. And it has all its structure constants as polynomials in P with integer coefficients. And so now at this stage, what you can do is you can turn this P into a T. So, so you can just, and then you can put T equals -1. And you can ask various questions about it. Right. So I don't know. I just said that. I haven't done it, but it's probably interesting. Yeah. Okay. So that's all about the Hall algebra. And now the main thing which I was supposed to do in this course is the following. So we are going to try to also enumerate flags of subgroups where we don't be ultra fussy about. So if you want to enumerate flags of subgroups where you specify the, the types of the subquotients, then you can do it using the Hall algebra, right? It's just you take, so you just take u mu, u nu, u eta, like I said, and look at the coefficient of u lambda in that, and that will tell you how to count the number of flags of subgroups, right? Where the filtered subquotients have types mu, nu, eta, and so on. And in fact, using this this principle here, you can actually make very explicit. You can write very simple code to compute these these polynomials g lambda mu nu p. Though I think there are better ways of computing them, so which is already implemented in Sage, so you don't really have to do that. But and I'll show you how to compute them in Sage also during the tutorial. But let me introduce one last problem, which is sort of begging for symmetric functions. So what I want to do is, I want to look at, so I have a group of type lambda, so AP lambda, which I'll just abbreviate to A lambda, and I want to count flags of subgroups. So, so let's say this is AM, AM minus 1, A0, and this is 0. So I'm just counting flags of subgroups. And all I'll specify is the cardinality of so I have some composition. So I'm saying that this is not a partition, these are just non-negative integers, maybe positive, well, non-negative integers, a weak composition uh, adding up to the size of lambda. And lambda is a partition of. So let's give this thing a name. I'll call it A. Let's call this number A lambda mu. And in combinatorics, when you have a bunch of numbers, as Christopher said, you try to make it a polynomial. You create a generating function. So, so I'll denote, so if this is mu, I'll say x to the mu is x1 to the mu1, xm to the mu m. And so instead of looking at these numbers in isolation, we will try to put them all together, and we'll define f lambda of x1 up to xm to be the polynomial sum over all mu a lambda mu x to the mu. So we just have a polynomial in m variables, and we can ask what is this polynomial, right? And hmm? ah, ah, okay, alpha lambda. Sorry. Okay, so what is this alpha lambda mu? What is this polynomial? Now, one very nice observation is that this polynomial is actually symmetric. Let's just think about the case where there are two variables, right? So if you're just looking at two variables, then you're saying mu1, mu2. So you're asking for the number of subgroups of order p to the mu1 such that the quotient is of order p to the mu2. But using our annihilator trick, we know that we can reverse these mu1 and mu2, right? So number of subgroups of order p to the mu2 such that the quotient is of order p to the mu1. And it's not difficult to show in the same spirit that by fixing the first I minus 1 and the last whatever, you can only play with two of the subgroups in the filtration and show that it is possible to interchange any two of the parts of this composition mu and still get the same answer here. So this is a symmetric polynomial. And so this takes us into the world of symmetric polynomials, and we could ask, what is this symmetric polynomial? So, could I take a few extra minutes?
You have a few extra minutes.
Okay, thanks. Maybe half an hour? No. Okay. No. Okay. No. Let's see. It would be more than 5, but a lot less than half an hour. So. Okay, so what I'll do is I'll briefly sketch how we understand these polynomials. And in that story again appears this Hall polynomial. So this Hall polynomial, we know it has, it's freely generated by U1 to the n. Now, those of you who have seen the theory of symmetric functions will be struck by the similarity between the kinds of symbols that are appearing in the Hall algebra and the kinds of things that appear in the study of symmetric functions. So let me just remind you of the things that appear in symmetric functions. The algebra of symmetric functions looks very much like the Hall algebra. So let me first define some McDonald style. So ET is just, so we'll fix some variables x1, x2, xn is just product I goes from 1 to m 1 plus xit. Okay, so you could ask yourself, what is the coefficient of t in this? The coefficient of t in this is just x1 plus x2 plus xn. What's the coefficient of t squared? Well, it's, you have to take pairs of distinct variables, right, and just add them up. So this is the generating function for elementary symmetric polynomials. So this is sum en x1, x2, xm e to the n goes from 0 to infinity, but in fact this turns out to be a finite sum. These polynomials will be 0 after n exceeds m. And similarly, there's this complete symmetric functions ht This is an honest infinite sum. Okay, so now what you do is, this h is freely generated by u1 to the n. It turns out that this, so I'll say lambda x1 xn, or I'll just call it lambda, is symmetric polynomials in m variables. So what you do is you define a homomorphism from the Hall algebra to by just taking this u1 to the n goes to So now instead of P, I will use a symbol Q just because it's more conventional in the symmetric function setting to use Q. Q raised to minus, let's say, minus n choose to En. So you just define it like this, right? It's a free algebra. You can send the generators wherever you like. Don't ask me why right now, but yeah, I can. So just take coefficients as polynomials, rational functions in Q. So then what happens, okay, so this is, just it's very easy where to send u1 to the n. But then it becomes very interesting. We ask, where does u lambda go? So phi of u lambda, well, this ends up being a polynomial in Q, and so all this is living in m variables and coefficients in uh, uh, rational functions in Q. So u lambda goes to some symmetric function with coefficients in rational functions in Q. So this polynomial is denoted by p tilde lambda, and it's got the variables x1, x2, xm, and it's also got this variable q. So yeah. And from what we've seen about the Hall algebra, this will actually define, these ENs generate the symmetric function algebra. So this will define an isomorphism from the Hall algebra onto the algebra of symmetric functions, right? And so these things form a basis for the algebra of symmetric functions. And the Hall Littlewood P functions are defined as P lambda x Q inverse is Q raised to n lambda P tilde lambda xq. Now this is a very annoying business that keeps happening because of this really annoying business that happens with these g lambda mu nu. The g lambda mu nu, what really stands out is the leading coefficient. But what we like when we work with polynomials is to set t equals 0 and see what happens, and that gives you the constant term. So this idea of taking the leading coefficient and turning into the constant term, that is achieved by this uh, this kind of transformation. I think the best reference for all this is McDonald's book, Symmetric Functions and All Polynomials, but I'll try to send out some notes later on because some of the things I've done a bit differently in these lectures to sort of, the development of the Hall algebra. But the proof in all essential points is the same. So, okay. So, huh? So let me just see. So if you put q equals 1, you will get complete symmetric functions, h lambda. P is q. Okay, so this will specialize to the complete symmetric functions, and here's the thing. So the symmetric functions have an inner product called the Hall inner product. So this is the inner product where H lambda. So h lambda is just h lambda 1, h lambda 2, h lambda L, and m mu. So what is m mu? This is a monomial symmetric function. So m mu is, so if you have a monomial x1 raised to a1, x2 raised to a2, xm raised to am, what you can do is you can just take these exponents and arrange them in weakly decreasing order and get a partition, right? So if that partition is mu, then you take this monomial, add all the monomials for which, after sorting the exponents, you get the partition mu. So this is just sum of x to the alpha, where alpha sorts. So this means alpha sorts to mu. So it turns out that you can define non-degenerate bilinear form on the symmetric algebra functions using this. So, so I'll just make the statement and maybe leave it at that. Let p lambda star denote the Hall dual basis of p lambda. So we have this basis p lambda. This is also a basis. P lambda tilde is a basis. P lambda is also a basis of p lambda. And this symmetric function is just p lambda star. These are called the modified. So it's very confusing because there's a lot of different places where there are different terminology. But slowly there's this website run by Per Alexanderson. He has a symmetric functions catalog online, which is really very useful. And there are two ways I refer to symmetric functions, either using Per Alexanderson's catalog or whatever the command you have to type into Sage to get it. So, so these are yeah, modified Hall Littlewood symmetric functions. Well, so you just extend it to Q. I mean, yeah, yeah. Just make it QQ linear. This is a basis over QQ, so you can. That's a definition. So maybe I should just stop here because the proof of this would probably take another 20 minutes or so. Yeah. I'll show you in the tutorial how we compute these things. We look at some examples. This beautiful theorem is due to Kirillov. It appeared in Contemporary Mathematics 254. So I should have said that. Yeah, it's not so easy to find. And 1998. Okay. You, or lunch. Yeah.